In Chapter 8, we looked at inferences from one sample, and we talked about testing claims regarding proportions and testing claims regarding means. However, in many cases, you're comparing two proportions or two means. For example, when you conduct clinical trials, you want to compare proportion of people who get sick who are given a drug versus the proportion of people who get sick who are given a placebo. So there's two proportions involved there. So that's where we're going in Chapter 9. A lot of the methods and procedures will be similar to what we did in Chapter 8, but we'll need a different test statistic, and some of the nuances will be slightly different. So Section 9.2, we're going to look at inferences about two proportions, and then in the next section, 9.3, we'll look at inferences about two means. But again, we'll talk about a p-value method and the critical value method in both of these proportions. And so first of all, let's look at the tools for testing a claim involving two proportions. First of all, the test statistic looks a little different than the previous test statistic in section 8.3 because we've got two proportions that we're dealing with. So we'll have two sample proportions, 1, 2, and then we'll have two population proportions. We also have this P bar and Q bar. P bar is called the pooled proportion. So if we've got two sets of people, a placebo group and an actual trial group, we want to add all the people who got sick, for example, in both groups, and add up the total number of people in both groups, and this will be what we call our pooled proportion, and we label that as P bar. Q bar, you can probably guess, is 1 minus P bar. And of course, N1 will be the sample size of the first group, and 2 will be the sample size of the second group. So for our purposes, the null hypothesis will always be that the population proportion for the first group equals the population proportion for the second group. So if you do a little algebra on this equality, we find that P1 minus P2 equals 0. So that means this P1 minus P2, for our purposes, will always be 0. And we can just consider the sample proportion for each group, P1 hat minus P2 hat. So our sample statistic that we'll use is this one down here. So let's look at an example. Given the data below, use a 0.05 significance level to test the claim that the fatality rate of occupants is lower for those in cars equipped with airbags. Of course, these days, every car is equipped with airbags, so this study was probably done many years ago when there was a transition from no airbags to airbags. So let me explain this table a little bit. The first row are the number of fatalities, and this will be either the fatalities where there is an airbag available in the car, and the fatalities here is the fatalities where there was no airbag in the car. The total occupants that we looked at in each of these cases where there was an airbag and where there was no airbag are given in the second row. So at first glance, it looks like they're fairly close because there were 41 fatalities when an airbag was available and 52 when there was no airbag available. But of course, if you look at the total occupants of those cars, then that changes these proportions. So what we're going to do is look at the proportion of people who were killed when there was an airbag available versus the proportion of people who were killed when there was no airbag available. Of course, you can maybe tell just by looking at this proportion was higher, certainly, when there was no airbag available. So what we're really testing is there enough of a difference between these two proportions to claim that, yes, airbags actually save lives, or could this just be a fluke in the data? So, step 1, just as before, we're going to identify the claim. But the claim, in this case, is that the fatality rate is lower for those in cars equipped with airbags. So let's first identify a P1 and a P2 and figure out which one applies to which proportion. So we're going to let P1 be the proportion of fatalities where airbags are available, just so we can keep the P1 and P2 separate. So P1 is where their airbags are available, and P2 will be proportion where there was airbags unavailable, no airbags available rather. So the claim is that the proportion of fatalities where airbags were available is less than the proportion of fatalities where airbags were available. So the opposite of that then is that P1 is greater than or equal to P2. And just as before, we're going to take the null hypothesis to be the one that has an equal sign and the alternative hypothesis to be the other one. So the null hypothesis here will be that P1 equals P2, and the alternative is that P1 is less than P2. So again, just as before, we can see that we're going to be dealing with a left-tailed test. The significance level in this case is given to us as 0.05. So step 5 will be to calculate the test statistic. And of course, since we're talking about two proportions, we have a different test statistic to use. So we need to figure some stuff out first. That is, figure out what P1 hat is, P2 hat, figure out the pooled proportion, this P bar, and then 1 minus that will be Q bar. So P1 hat is the proportion of fatalities when there was an airbag available. So we take the number of fatalities, divide them by the total number of occupants where there was an airbag available, and that gives us our P1 hat. P2 hat then is done the same way, but using the no airbag available data. P bar, what we're going to do to calculate that is add up the number of fatalities together, and that'll be in our numerator. Then add up the total number of occupants together, that'll be our denominator, and then finally divide that to give us our pooled proportion, 0.0043. Q bar then will be 1 minus that, 0.9957. So now that we've done all these preliminary calculations, we can plug everything into our test statistic, and this comes out to be negative 1.91. So just to be sure, let me go through this. My P1 hat was the proportion of fatalities when there was an airbag available. My P2 hat was the proportion of fatalities when there was no airbag available. Then I've got my pooled proportion and 1 minus pooled proportion down here. Each then of these are going to be divided by the individual sample sizes. So considering these as two different samples with two different proportions, my first sample size is 11,541 and my second sample size is 9,850. So step 6 is to determine the p-value. Now keep in mind, since we're talking about proportions in this section, we're going to be using the normal distribution table. So because this is a left-tailed test, we just need to find the area to the left of our test statistic, negative 1.91. So double check, look at your normal distribution table and make sure you agree the area to the left of negative 1.91 is 0.0281. Now keep in mind, if this was a two-tailed test, we would double this p-value, but since this is a one-tailed test, we're going to leave it alone and call our p-value 0.0281. So do we reject the null hypothesis? Well, since 0.0281 is less than our significance level 0.05, we can reject the null hypothesis. So keep in mind, our null hypothesis was that the proportions were the same, but our claim was that P1 is less than P2. So, since we rejected the null hypothesis, it does appear that we have enough evidence to support our claim that the proportion of fatalities is less when you have airbags than it is when you do not have airbags available. Let's take a look at another example. In 1993, the survey of 560 college students, 171 said they used illegal drugs during the previous year. In a recent survey of 720 college students, 263 said they used illegal drugs during the previous year. Use a 0.05 significance level to test the claim that the proportion of college students using illegal drugs in 1993 was the same as it is now. So our claim then is that the two proportions, the 1993 proportion and the current proportion, are equal. So let's first of all identify one of them to be labeled P1. So in this case, I will call P1 to be the proportion of college students using illegal drugs in 1993. That means P2 will be the proportion currently. So the claim is that the two proportions are equal. The opposite of that claim then is that P1 does not equal P2. So our null hypothesis will be the one that says equals in it, and the alternative will be the other one. So in this case, we are dealing with a two-tailed test because we're using the not equal sign in our alternative hypothesis. So step 4, we're going to identify the significance level, but of course this is again given to us as 0.05. So step 5, we want to calculate the test statistic. So first of all, just as we did in the previous problem, let's get all the preliminary calculations out of the way. P1 hat is the proportion of 1993 students who said they used illegal drugs. That is 171 divided by 560. P2 hat is going to be 263 divided by 720 because P2 is the current year college students. So P hat is going to be the pooled proportion, adding up the two numerators together and adding up the two denominators together to get a pooled proportion of 0.391, which means Q bar will be 0.6609. So now we can throw all this into our test statistic. We get a test statistic of negative 2.25. Now keep in mind, this is a two-tailed test. So when we calculate the p-value, since this is a negative test statistic, we're going to find the area to the left of it, but we need to double that. So to determine the p-value, since our test statistic is negative, we're going to find the area to the left, and we find that to be 0.0122. Verify this on your own normal distribution table, that the area to the left of negative 2.25 is 0.0122. But since it's a two-tailed test, we want to double that, so our p-value is 0.0244. For step 7, we just simply compare this p-value to our significance level 0.05. Since our p-value is less than our significance level, we're going to reject the null hypothesis. So to interpret this, since our claim was that P1 equals P2, which was the same as our null hypothesis, and since we rejected the null hypothesis, it does appear that we have enough evidence to reject the claim that the proportion of college students using illegal drugs in '93 was the same as it is now. So, in other words, we've shown from our results that there is evidence that the proportion of students using drugs now is different than the proportion of students using drugs then. So let's take a look at some examples using the critical value method. Chantix is a drug used as an aid to stop smoking. The numbers of subjects experiencing insomnia for each of 2 treatment groups in clinical trial of the drug are given below. Use a significance level of 0.01 to test the claim that the proportion of people in the Chantix treatment group who were insomniacs is equal to the proportion of people given a placebo who are also insomniacs. So step 1, let's identify the claim, but of course in this case the claim is almost directly given to us. P1 is equal to P2. But let's pick one group to be P1 and the other group will be P2 just so we can keep things straight. So let's let P1 be the proportion in this Chantix treatment group. So P1 will be the Chantix treatment and P2 will be the placebo group proportion. So the claim is that P1 equals P2. The opposite then is that P1 does not equal P2. Let's identify the null and alternative hypothesis, but of course The null hypothesis will be the one with the equal sign. The alternative will be the other one. So again, we're dealing with a two-tailed test in this case. The significance level in this case, though, is going to be 0.01. So step 5, we're going to calculate the test statistic. Let's get P1 hat and P2 hat, and P bar and Q bar. So P1 hat we said was the treatment group, so this will be the 19 divided by the 129 people in the group. P2 hat then is the 13 in the placebo group who were insomniacs divided by the 805 people who were in the placebo group. P bar is the pooled proportion, so the numerators added together divided by the denominators added together, and I get 0.0343. Q bar then is 1 minus that. Now we can plug all this into our test statistic, and we get a test statistic of 7.6. So step 6, we're going to determine the critical value. So we do this by looking at the significance level, but we have to keep in mind that since this is a two-tailed test, we divide that significance level equally between the two tails. Thus, we need a positive and negative critical value with 0.005 to the right and left, respectively. So in other words, we need a positive critical value that has 0.005 to the right and a negative critical value that has 0.005 to the left. So if you look this up on your normal distribution table, you should find that the critical value negative 2.575 has 0.005 to the left, and the positive critical value 2.575 has 0.995 to the left, which means it has 0.005 to the right. So these are our critical values. Step 7 then is to compare our test statistic to our critical value. Now, since this is a positive test statistic, we're going to compare it to the positive critical value. Since it's greater than the positive critical value, that means it's more extreme, which means we can reject the null hypothesis that the two proportions are equal. So our claim was that the proportion of insomniacs in the treatment group is the same as the proportion of insomniacs in the placebo group. That's the same as the null hypothesis, which we rejected, so we can say there's sufficient evidence to reject the claim that the probability you will have trouble sleeping is the same with and without using Chantix. In other words, it does appear that Chantix has some effect on how well you sleep or whether or not you're an insomniac. So take a look at this example. A Pew Research Center poll asked randomly selected subjects if they agreed with a statement that it is morally wrong for a married couple to have an affair. Among the 386 women surveyed, 347 agreed with the statement, and among the 359 men surveyed, 305 men agreed with the statement. Use a 0.05 significance level to test the claim that the percentage of women who agree is greater than the percentage of men who agree. Does there appear to be a difference in the way women and men feel about this issue? So, first of all, let's identify the claim. We're testing the claim that the percentage of women who agree is greater than the percentage of men who agree. Or, another way to say that is the proportion of women who agree is greater than the proportion of men who agree. So, if we call P1 the proportion of women who agree, then what we're saying by our claim is that P1 is greater than P2. So the opposite then is that P1 is less than or equal to P2. Our null hypothesis comes from the one that has an equal, and the alternative will be the one that does not have an equals. So now we're dealing with a right-tailed test. The significance level in this case, of course, is 0.05. Step 5 then, we're going to calculate the test statistic. So again, we're going to calculate P1 hat, P2 hat, P bar, and Q bar. So I get 0.888990 for my proportion of women who agree with the statement. 0.8496 is the proportion of men who agree with the statement. P bar was 0.8752, and Q bar then is 0.1248. So before we calculate the test statistic, let me just point out that in both cases, men and women, there is a significantly larger percentage of men who agree with the statement than men who do not agree with the statement, and same for the women. There's a significantly larger number of women who agree with the statement than do not. But of course, what we're testing is the percentage of women, or the proportion of women who agree, greater than the proportion of men who agree. Now, just based on our sample, that appears to be the case. But of course, what we're doing in all these sections since Chapter 8 is looking at our test data and saying, is that difference enough to say that this must be true for, or this may be true for the entire population? So let's throw these into our test statistic, and I calculate this to be a test statistic of 2.04. So let's find the critical value based on a 0.05 significance level. And keep in mind, this is a right tail test, so we don't divide the significance level equally between the two tails. We just need the critical value that has 0.05 to the right, which is the same as the critical value that has 0.95 to the left. So look up in the normal distribution table, you should find that the z-score that has 0.05 to the, 0.95 to the left is 1.645. And that, of course, is the critical value that has 0.05 to the right. So, if that's our critical value, do we reject the null hypothesis? Well, our test statistic was 2.05, and that is greater than the critical value. So since this is a right tail test, and our test statistic was greater than our critical value, we're going to reject the null hypothesis. So our claim was that the proportion of women who agreed is greater than the proportion of men who agreed. Our null hypothesis was that the proportions were equal, but we were able to reject this null hypothesis. So that appears that based on our sample, there is sufficient evidence to support this claim that the percentage of women who believe it's morally wrong to have an affair is greater than the percentage of men who agree with the statement. So it does appear that there is a difference in the way women and men feel about this